Good morning, students. So we have come to the end of the second unit, complex number. We are going to deal something on applications of complex number. So we discussed earlier about some applications of complex number which are used in the gravitation field and the path of satellites and all those things we discussed. However, we will have to go with Laplace equation. In fact, Laplace equation which we studied already in electrostatic potentials. In undergraduate physics, you would have studied in electrostatic potentials about the Laplace equation. So this is your Laplace equation. Del squared phi equals 0. So this is your Laplace equation, and that's called a Laplacian. Suppose if it is not equal to 0, what we call this as Poisson equation. So del squared phi is not equal to 0, it has some other number like rho. Then we say that that equation is nothing but Poisson equation. Okay, but we are not going to deal anything with the Poisson equation because del squared phi equals 0 is much more important, because the real and imaginary part of analytic function will satisfy the Laplace equation. That's the reason that in complex number the del squared phi equals 0 is given much more important. I repeat, the real and imaginary part of analytic function will be satisfied by Laplacian equation, del squared phi equals 0. The solution of del squared phi equals 0 will give you real and imaginary parts. So it's nothing but a complex number. And the theory of solution of this equation is known as potential theory. So application is nothing but potential theory. And under potential theory, we are going to have two applications. One is about electrostatic potential, then another one is about heat problems. So we are going to have discussion on both the things. One is on electrostatic potential and another one is heat problems. And in both the problems, we are going to have a complex number. This complex number is called complex potential. So usually complex number consists of both real part and imaginary part. We know already, correct? And this complex potential, which we are going to deal with in all the applications like electrostatic potential and heat problems, what we call this as complex potential. This complex potential consists of both real part and imaginary part. Is it okay? So complex potential is nothing but a complex number in the application, and which consists of real part and imaginary part. Real part in electrostatic potential is termed as equipotential. Equipotential. Whereas the counterpart, the complex conjugate of real part, which is nothing but lines of force. So in electrostatics, complex potential is a combination of equipotential and lines of force. We are going to deal, okay, no problem. And in heat problem, the same complex potential, complex heat potential, this is termed as complex heat potential, which is a combination of, as I said earlier, and this is vector potential and heat flow flux, heat flow lines. So with this introduction, we are going to start with two applications. One is about electrostatic potential and another one is heat problems. Okay. So as I said earlier, that Laplacian equation is very important, especially while dealing with applications of complex numbers. So del squared phi equals 0 is one of the most important partial differential equations in engineering mathematics, because it occurs in connection with the gravitation field, electrostatic fields, steady state heat conduction, incompressible fluid flow. So out of all the four applications, we are going to mainly deal with electrostatic fields and steady state heat conduction. So which are there in the syllabus. So the theory of solutions of this equation is called potential theory. The two-dimensional Laplace equation is given by this. So we know about the Laplace equation, which is given by two-dimensional. Del squared phi equals d squared phi by dx squared plus d squared phi by dy squared equals 0. Okay, this is two dimension. The force of this is about electrostatic application. So we are going to have the first application, which is on electrostatic fields. The force of attraction or repulsion between charged particles is governed by Coulomb's law. We know already. So Coulomb's law between two charges is given by, we know already, F equals 1 by 4 pi epsilon naught q squared by r squared. We know already. So two charges, it can be a repulsion or it can be an attraction, both. So between charged particles governed by Coulomb's law. And of course the force which is given as the negative gradient of the function, potential, that also we know already. F equals minus del V. V stands for potential. F equals minus del V. This force can be expressed as a gradient of the function. So this is called a gradient. Del is nothing but partial d by dx. Okay, I partial d by dx plus j partial d by dy plus k partial d by dz, we know already. So del. So that's called a gradient of the function. And this is called the electrostatic potential. Okay, so now what I am going to do is, I am going to dot product with on both sides by del. So del dot F equals minus del squared F, correct? So if we have any dot product on both sides with del, so that will give me del dot F equals minus del squared F. So del dot F equal to 0, gradient of force equal to 0, then this becomes del squared pi equals 0. So which is nothing but Laplacian equation. So that's the idea. Which is nothing but del squared pi equals 0. So Laplacian equation. So the electrostatic potential satisfies Laplace equation. Del squared pi is given by this, and E is perpendicular to the equipotential surface. Because when you take a charge, the lines of force will come exactly radial outward. Suppose we are going to have the potential at the top, then the potential, it will be equal on the surface. So what we call this as equipotential. You have lines of force which will be coming like this. Here the potential will be constant. Here the potential will be constant. So what we call this as equipotential surface. So equipotential surfaces. The surfaces phi is constant are called equipotential surfaces. This phi will be real part and some analytic function. So as I said earlier, in electrostatic fields, we have f of z is termed as complex potential, which is a combination of real part and imaginary part. Okay, and real part is termed as equipotential. And imaginary part, this is the counterpart, complex conjugate of real part, is termed as lines of force. So this is where lines of force. So complex potential is the combination of equipotential and lines of force. Lines of force which are coming out and they are perpendicular to the equipotential surface. Okay, and they should satisfy Laplace equation. Of course, they should satisfy Laplace equation. That's why we have taken Laplace equation. Okay, and f of z analytic function that can handle both equipotential and lines of force simultaneously. So one is a real part, another one is a imaginary part. Okay, so it's an analytic function which is a combination of real part and imaginary part, and they should satisfy Laplace equation. Or otherwise we can say the solution of the Laplace equation is nothing but real part and imaginary part. So we can say either way. So one is nothing but your equipotential, which is the real part. Another one is lines of force, which is nothing but imaginary part, which is a complex conjugate of this. And of course, we'll have to use CR equations, Cauchy-Riemann equation. Surely we'll have to implement. Okay. This is exactly what we studied, like z equals x plus iy. So we know already that any complex number is nothing but x plus iy. We have already studied. So this function f of z. So f is called as complex potential, which corresponds to the real potential, and the conjugate of this that will give us lines of force. And it has got f has got two advantages. One is a technical one because it contains both real part and imaginary part. Another, the physical one is nothing but it should satisfy Laplace equation, and f of is an analytic function. We can have simultaneously the results of equipotential and lines of force. Suppose if we have any one, we can use CR equation to get another one. We have already studied this technique. If you know this one, we can use CR equation to get the real part. So which we are going to see now. Okay. Now this is just to recap. This is for the fluid dynamics. So earlier we discussed about electrostatic fields, and this is for the fluid dynamics. This is another application. And again the analytic function, which is a combination of velocity potential and streamlined potential. Streamline means, see, we have the water flow, that's called the stream, turbulence and streamline. Can you remember? So this is your streamline. Since complex potential f of z is analytic, then phi and psi, real part and imaginary part, are harmonic functions. Del squared phi equals 0, that will always will lead us the harmonic function. Can you remember this word which we discussed in one of the problems in complex number earlier? So harmonic function, which satisfy Cauchy-Riemann equation. Okay, it has to satisfy CR equation, and this is your CR equation using phi and psi. Using phi and psi, this is your CR equation. d phi by dx, which is equal to d psi by dy. Okay, and d phi by dy, which is equal to minus d psi by dx. So this is your CR equation. See here, and of course we know CR equation earlier. Z is in terms of the complex one in terms of u plus iv. Can you remember this equation? CR equation. So du by dx equals dv by dy. Du by dy equals minus du by dx. This is exactly the same thing. Here we have used different notations. That's all. This is the ordinary one. Z equals u plus iv. Here it is nothing but f of z w equals phi plus I psi. This is your phi. This is your psi. Okay. So complex electrostatic potential. Since phi is harmonic, there exists a harmonic function psi, which is the conjugate of your phi, such that the complex potential is a combination of equipotential and lines of force. Is analytical in any region not occupied by the charge. The function gamma of z is called a complex electrostatic potential. If it is in heat, we will say complex heat potential. If it is in electrostatic potential, we will say complex electrostatic potential. Okay. So this is a function, complex function. The curve phi of x comma y is nothing but alpha and psi is nothing but beta are called equipotential lines and the lines of force respectively. The lines of force cut the equipotential, as I said, perpendicular. See, as I said earlier, they cut orthogonally. Now this is the first question, very important question. We are going to have the applications of complex number, potential between parallel plates. So you are going to have a parallel plate now. Both are charged. Okay, and one is at the distance x equal to -1, another one is at the distance x equal to 1. Parallel plates. And this is u1 of x and this is with the potential u2 of x. U is somewhere here in between. And this is your x axis and this is your y axis. Okay. Now, so in that case, the lines of force only will move in the x direction, from x equals -1 to x equals +1. Is it okay? The lines of force will move only in the x direction. So let us consider two parallel conducting plates extending to infinity, which are kept at potentials u1 and u2 respectively. Then from the shape of the plates, it follows that u depends only on x. Just now I said the lines of force only in the x direction, so it depends only on x. So we can use Laplace equation now. So del squared E equals 0. So which is nothing but uxx means d squared u by dx squared. So it's a different notation. You'll have to learn in different books, they follow different notation. Uxx means d squared u by dx squared, which is equal to 0. Okay, so this is exactly, the notation is exactly like this. Okay, suppose if u of x equal to ax plus b, you just differentiate with respect to x, that will give you du by dx equals ax. D squared u by dx squared will give you a. Is it okay? I repeat, you differentiate this, that will give you ux will give you ax. Uxx will give you a. Is it okay? See, uxx. So uxx plus uy, this is Laplacian equation which we have written here. And when you are going to differentiate again, that will give you d squared u by dx squared will be equal to 0. So your ux only once if you, so that will give you ux equals a, and a, b are determined by the boundary conditions. We are going to have boundary conditions which is nothing but x equals -1 at u1 and at u2 x equals at x u2 at x equals 1. So ux equal to ax plus b. Now substitute x equals -1 here. At u1, see we know u1 at x equals -1. When you are going to substitute, that becomes minus a plus b. When you are going to substitute x equal to 1 here, for u2, u2 becomes a plus b. When you are going to add these two, as I said, a and b can be determined by the boundary conditions. So these are all boundary conditions. We are going to find out a and b in terms of u1 and u2. So you add these two, a will cancel. You will have 2b, correct? And 2b by 2, that will give you b. So b is in terms of u1 and u2. So we have determined now b. Suppose when you are going to subtract, you will get minus 2a. So instead of b will get cancelled. You will get, when you are going to subtract, you will get minus u1 plus u2 by 2, which is equal to a minus b plus a plus b divided by 2. That will give you 2a by 2. 2 get cancelled. A is in terms of u1 plus u2. And of course, we have found out now a and b in terms of u1 and u2. Correct? We have found out now. You substitute here. So we will get 1 by 2. See here, we will get instead of a, you substitute here. Substitute this expression. Instead of b, you substitute this expression. So you will get this. So that will give you the complete one. As I said earlier, a and b can be determined by means of boundary conditions. So they are all boundary conditions we have used. Hence the potential of the field between two given plate is given by this expression. See, there is no a here, there is no b here. Everything is in terms of u1 and u2. u1 is the potential at the first point, u2 is the potential at the second point, x equal to 1. So the equipotential surfaces are parallel lines. So they are all parallel lines. And in terms of complex conjugate, vx comma y is a conjugate harmonic function, ux is a normal one. Then it's given as u equals ax plus b, where a is given by this, b is given by this. Okay, under CR equation, Cauchy-Riemann equation, which is given by partial du by dx equals dv by dy, and partial du by dy equals minus dv by dx. Correct? And you know already u of x equal to ax plus b, we know already. Now du by dx. What is du by dx? You differentiate du by dx. Here it is, du by dx. What is the answer? A. Du by dx equal to dv by dy. So dv by dy equals a, correct? As I said earlier, if you know the real part, using Cauchy-Riemann equation, we can find out the imaginary part and vice versa. Okay, so now du by dx we have found out from that equation, and we know that dv by dy is given by a. So your dv equals a dy. Integrating on both sides will give you, integrate on both sides will give you v equals a, integration of dy will give you y plus your integration constant should be there, some integration constant. That constant is nothing but c, again which depends on only on x, because lines of force going from x direction. So that's the reason x. Now dv by dx, we have to find out the another one. So dv by dx is nothing but your c of x, which is nothing but c of this becomes 0. So this is your c of x, and of course this is equal to 0 we know already. So v can be easily found out. So v equals ay plus cx. So a, so your a is given by this, your y is here, and c is here. Earlier we started with u, can you remember? We ended up with u. Now we have obtained v. So u plus iv will give you complete complex function. That's all. Okay. So u plus iv, which is nothing but your complex potential, which is equal to, instead of u substitute ax plus b, instead of v substitute ay plus cx. See here, ay plus c. And of course we know that ax plus iay, b plus c, you just combine these two, ax plus IAY, you pull A out. So A x plus IY, x plus IY is nothing but Z. So A is Z, you combine the constants P plus B plus IC. Is it okay? So your complex potential is simplified as AZ plus B plus IC. The lines of force is given by AY plus C, which is equal to A is constant. These lines are always parallel to the x-axis. Okay, so that's the idea about parallel plates. Now you go for